Greetings, scholars. Here we're going to be working on section 2.4, complex numbers. A few learning objectives. One, in this section you will add and subtract complex numbers, multiply and divide complex numbers, and simplify powers of I. Optimizing AC circuit performance. In electrical engineering, complex numbers prove indispensable for analyzing AC circuits. They efficiently represent impedance, incorporating both resistance and reactance from capacitive and inductive elements. Engineers leverage complex arithmetic to optimize power factors, enhancing energy efficiency in circuits. This practical application highlights how complex numbers streamline analysis and empower engineers to design more efficient electrical systems. So basically, a complex number, it's like an extension of the reals, all right? So the reals are like what we're used to. The real numbers is just basically the intersection of all like rational and irrational numbers. And so I guess mathematicians were working on like a new idea or concept or whatever, where like they needed something such that when you take the square root of it, you get -1, right? And there's no real number that does that. If you square, you need it so that when you square something, you get a negative result. I think whatever I said a minute ago may have been a little bit off. But yeah, they needed a number such that when they square it, they get -1. So if you have something squared equals -1, you take the square root on both sides. So then they created a lot of times in mathematics, when something doesn't exist, you just give it a name and create a new system. And so that's kind of what happened there. So then they created the imaginary number I, which equals the square root of -1. And so that's what this section is about. Imaginary and complex number. A complex number is a number written in the form a plus bi, where a is the real part of the complex number and b is the imaginary part of the complex number. If b equals 0, then a plus bi is a real number. If a equals 0 and b is not equal to 0, the complex number is called a pure imaginary number. An imaginary number is an even root of a negative number. So given an imaginary number, express it in the standard form of a complex number. Write the square root of -a as the square root of a times the square root of -1. Express the square root of -1 as I, and write this, and then we write square root of a times I in simplest forms. So we have the real part versus the imaginary part. Okay, let's see if we can see this in action. So we're asked to express this in standard form. Okay. So let me see. I'm going to rewrite this. We got the square root of -9. This can be rewritten as the square root of 9 times the square root of -1. All right. Square root of 9 is 3. And what we just introduced today is that the square root of -1 is I. So then this is going to be the standard form. So it's 3i. Oh, okay. 0 plus 3i. There. That's fine. So the complex plane, in the complex plane, the horizontal axis is the real axis and the vertical axis is the imaginary axis, as shown in figure 3. So given a complex number, represent its coordinates on the complex plane. 1, determine the real part and the imaginary part of the complex number. Move along the horizontal axis to show the real part of the number. Move parallel to the vertical axis to show the imaginary part of the number and plot the point. So we're asked to plot this complex number on the complex plane. So if we have 3 minus 4i, then we're going to go right 3 and down 4, so it should be here. Adding complex numbers, we basically add the corresponding components. So the real part adds with the real part, the imaginary part adds with the imaginary part. And with subtracting complex numbers, we just have to be sure to distribute that negative into the second complex number and then subtract the real parts plus subtract the imaginary parts. So add or subtract is indicated. So for instance, for part A, 3 plus 2 ends up being 5. Negative 4 plus 5 ends up being 1. So that's just I. I'm going to rewrite part B. So we have this negative 5 plus 7i. If we distribute that negative, that's going to become plus 11 minus 2i, right? That way we have an easier time of keeping track of our signs. So then negative 5 plus 11 is 6. 7 plus negative 2 is a positive 5. So it should be 6 plus 5i. So 5 plus I and 6 plus 5i. And those are correct. Okay. So here we can just distribute, right? So then 4 times 2 becomes 8. 4 times 5 is 20. Okay. All right, so here we would want to FOIL. Let me start by getting a copy. So we have what? 4 plus 3i times 2 minus 5i. All right. So then we can say first times first, outer times outer, inner times inner, and last times last. Okay. So first times first is going to give us 8. Outer times outer is going to be a negative 20i. Inner times inner is what? Plus 6i. And last times last is minus 15i squared. Okay. Now I squared, remember I is the square root of negative 1. So then if you square root, it cancels. So that I squared is just negative 1, right? So negative 15 times negative 1 is a positive 15. So those, if we combine like terms, it gives us what? 23 there. Minus 14i. 23 minus 14i. Okay, and here's just a typed version of what we just did. So the complex conjugate of a complex number a plus bi is going to be a minus bi. It's found by changing the sign of the imaginary part of the complex number. The real part of the number is left unchanged. When a complex number is multiplied by its complex conjugate, the result is a real number. When a complex number is added to its complex conjugate, the result is a real number. Okay, that's interesting. So here we're asked to find the complex conjugate of each number. So for A, we're given 2 plus I times the square root of 5. So then its complex conjugate is going to be 2 minus I times the square root of 5. And then for B, we have a negative 1/2 I, so its complex conjugate should be a positive 1/2 I. Thank you. Okay, I think what we have is fine. Yeah. So although we have seen that we can find the complex conjugate of an imaginary number, in practice we generally find the complex conjugates of only complex numbers with both a real and imaginary part. To obtain a real number from an imaginary number, we can simply multiply it by I. Okay. Let's see here. So we're asked to divide the first one by the second one. Okay. So I'm going to rewrite it. 2 plus 5i over 4 minus I. So remember, I is the square root of negative 1, and generally we don't leave radicals in the denominator. So what we're going to do to rationalize this guy, in other words, we're going to multiply by some form of 1 to get rid of the radical in the denominator. So we're going to multiply by 1 in the form of the conjugate over the conjugate, right? So the conjugate of the denominator. Right, again, we're going to multiply by 1 in the form of 4 plus I over 4 plus I. All right. So anything divided by itself is 1, essentially. And then let's just do this multiplication and see what happens. All right. So on top, it looks like we need to FOIL. So first times first gives us 8. Outer times outer gives us plus 2i. Inner times inner gives us what? Plus 20i. And last times last gives us plus 5i squared. On bottom, if we do the same thing, first times first is 16. Outer times outer is plus 4i minus 4i minus I squared. Okay, I'll continue working here. So I squared is -1. So 8 minus 5 is a 3 plus 22i over I squared is -1. Double negative is a +1. So that's a 17 on bottom. This cancels this. Okay. All right, let's keep going. And then I want to say, oops. Usually we'll go ahead and split that apart. Come here, come here, come here, come here. Come here, come here. Come on. Come on. Because I don't need you losing your mind. All right, so we can split this apart as 3 over 17 plus 22 over 17i. Yep. Okay. All right. So I'm gonna do. Man, Malachi. Let's see. Hopefully it still works. She just like tore all my shit up. I don't know if it. Okay, good. Okay. Whew. Somebody just came to the house. The alarm went off. My dog usually goes in the middle of a recording. I don't know. It always happens. Like I'm always in the middle of a recording, and so I grabbed her so she wouldn't go crazy. But then when I put her down, she like ripped my microphone apart in an instant. I'm like, how did that happen? So I had to put it back together. Okay. Anyway, so we're going to simplify powers of I. All right. So let's look at I to the power of 1. That's just what? The square root of -1, right? Okay. Now let's consider I squared. Well, that's going to be what? The square root of -1 squared, right? But then square root squared, they cancel. So then this is just going to be -1. So then let's look at I cubed. That's going to be the same as I squared times I. But I squared is -1, so then this is ultimately -I. And then I to the power of 4. Well, that's the same as I squared times I squared, which is -1 times -1, which is just 1, right? So then let's look at power of 5. Well, I to the power of 5 is the same as what? I to the power of 4 times I, which is just going to be I to the power of 6 is what? I to the power of 4 times I squared. So that's just a 1 times -1, which is ultimately -1. I to the power of 7 is I to the 4 times I to the 3, which is 1 times -I. And then I to the power of 8 is I to the power of 4 times I to the power of 4, which is just 1, right? And so hopefully you can see that the powers just keep repeating every power of 4. So every time you get to a multiple of 4, it repeats, right? And so, you know, you can go in either direction, right? So this powers of I. And I think we just have a type version of that here. Okay. So here we're asked to simplify, we're asked to evaluate I to the power of 35. Okay. So I think for these, we want to find the largest multiple of 4 less than 35, right? 8 times 4 is what, 32, and 9 times 4 would be 36. So we're going to rewrite this as what, I to the power of 32 times I to the power of 3, because I think it's 3 left over. So then I to the 32 is 1, and I to the power of 3. So all of this boils down to negative I. Again, this every time we get a multiple of 4, that's really just 1, and then it's one of the, from there it's just one of the four results that we saw in the previous slide. And negative I is correct here. Okay. Can we write I to the power of 35 in other helpful ways? Factorization of 35. I'm not seeing that one. Why that one? Reduced form. Each of these will eventually result in the answer we obtained above, but may require several more steps than our earlier method. Okay. I mean, that's fine. Yeah, I guess these are just other ways of writing it, but eventually we're still going to get to the same result that we had before. Okay. All right, with that, we're going to end the session here, and from one beautiful mind to another, take care. Peace.